Hey everyone, welcome to another session of CeerazzleDazzlePhysics. In today's session, we're going to be talking about using the discharge equation Qt is equal to Q0 e to the minus t over RC and using learn functions, guys, to help rearrange it. Okay, so before we start, make sure you've watched my other videos in this scheme of work, otherwise it just won't make sense. I prove how we actually obtain the discharge formula and I explain why it looks that way in two separate videos, so make sure you watch them before we watch this one. Right, so let's just have a quick recap before we move on. Okay, so here I have a simple circuit on the left-hand side. It is a capacitor and a resistor with a switch separating them. Yeah, so right now they're not connected. Yeah, the switch is not on. But the question is the following. What happens if I was to hit the switch? So if I was to hit the switch over here, what's going to happen? So the switch will be hit right now. Obviously, the charge will start to flow around the circuit. So the charge starts to flow around the circuit over here. There we go. So yes, look, my electrons start to flow around from the negative terminal, or because there's a concentration of electrons, all the way around here. So therefore, what happens to the charge stored on my capacitor? Obviously, it is discharging, so the charge is getting less and less. So if I was to plot a graph of charge against time, we end up with the following graph. There we go. There we go over here. This graph is exponential. It's exponential here. Okay, so from this graph, we can then get the equation to define the discharge of a capacitor. It will be Q at time t will be equal to Q0 e to the power of minus t divided by R times by C. Qt is equal to Q0 times by e to the power of minus t over RC here. Let's define all of these bits over here. So if you've forgotten, we'll put them over here on the right hand side. Okay, so as you can see, I've added it right now. Q0 is the initial charge at time t is equal to 0. So the initial charge at time t is equal to 0. Qt is the charge on the capacitor at time t. So after a certain amount of time has passed. R is the resistance in the circuit and C is the capacitance here. So in terms of what we can see on the graph, this point over here is obviously the charge at time t equals 0. So obviously this is the initial charge, so this bit over here will be Q0, the initial charge over there. This formula is useful because obviously let's say somebody asks you, oh, what would the charge be after 10 seconds? What would the charge on the capacitor be after 10 seconds? We can now work it out. So obviously it's a really useful formula. We can work out the amount of charge stored on the capacitor after a certain amount of time has passed. Right, so here's a question to get us thinking. Okay, so let's test our understanding with the following question. How much charge is stored on a capacitor after 25 seconds? How much charge is stored on a capacitor after 25 seconds? If the resistance is 400 ohms and the capacitance is 1000 microfarads and the initial charge is 50 millicoulombs. So 50 millicoulombs, guys. So how much charge is stored? Well, what it's really asking you is the following. We're trying to find out the charge Qt. We already have Q0 because Q0 will be equal to 50 millicoulombs. Yes, the initial charge. There we go. We also have the capacitance value of 1000 microfarads. So microfarads over here. And also we have the time of 25 seconds over there. And the resistance value going to be 400 ohms. Okay, so using our formula then, we know that Qt is equal to Q0 e to the minus t divided by RC over here. Q0 is obviously 50 millicoulombs, so it's going to be 50 times 10 to the minus 3 over there. Yes, millicoulombs, converted it to coulombs, and we're going to use the E function over here to make sure you're happy to use it on the calculator. Spend time working on that. I might do a video on that as well. E to the minus t, and t is going to be, what was the time? 25 seconds, divided by the resistance, 400 at the bottom, and times by 1000 times 10 to minus 6. Yeah, that's all to the power of, e to the power of all of that, e to the power of all of that. Okay, so on the calculator, it will look like the following. So the charge at 25 seconds, subscript 25 over here will be equal to, okay, so I'm getting this value, guys, on my calculator. The charge stored after 25 seconds will be 3.59 times by 10 to the minus 29 coulombs, guys. So make sure you can do that yourself, guys. Get your calculator out, make sure you can do that yourself. Okay, so that's one example we've now done. So now we've had a use of that formula here. So if somebody asks you what charge is stored on the capacitor after a certain time, we can now use that formula, provided that you know the resistance, the capacitance, and the time and the initial charge here. Alright, okay, so we have three more formulas you should be familiar with. And don't worry, if you don't understand where I've got them from, in that previous video I'll walk you through it. We have the charge at a certain time is equal to Q0 e to the minus t over RC. The voltage at a certain time is equal to V0 e to the minus t over RC. And the current at a certain time is equal to I0 e to the minus t over RC. These are all equations for discharge. Yes, all equations for discharge here. Make sure you're familiar with them because you might be sometimes using the charge, sometimes the voltage, sometimes the current. And look guys, we have that graph here, they're all the same. They're all the same. For discharging though, they're all the same for discharging. Okay, so before we move on, we're going to talk about rearranging the formula. Rearranging the formula. So now guys, we've got to use natural logarithms. Yes, so natural logs and the Lund function here. So let's say for example, it's quite easy to make V0 the subject of the formula. But let's say somebody says to you, can you make the resistance the subject of the formula? What will the resistance be equal to? We've got to rearrange this formula to make R the subject, but we've got to use Lunds now. So we'll do it very slowly. So we know that Vt is equal to V0 e to the minus t over Rc. And obviously you have to check your maths because make sure you're able to rearrange it, yes? So you're going to have to Lund both sides here. So what I do is the following. I take the V0 underneath, so I know Vt divided by V0 on this side here is equal to e to the minus t over Rc. Happy? Now from here I'm going to Lund both sides. So I'm going to Lund both sides to get rid of the e. So the Lund of Vt over V0 is equal to, okay, on the right hand side what happens is this exponent pops down, so minus t over Rc drops down, times by Ln e over here, Ln e. So that whole exponent pops down and I'm learning the e over here. So that's how I can able to drop it down using the Ln function here. Now from here I can then rearrange it and then we can have the following. So from here we can then rearrange it. We know that Ln e also, this term over here, Ln e is equal to 1. So Ln e is equal to 1. So therefore we end up with Ln, open bracket, Vt over V0 is equal to minus t over Rc over here. Minus t over Rc over here. Then, if I really want to, I can then rearrange it. I'll take the R up and I'll shift all of this underneath. Therefore we have R is equal to minus t over, and look, C times by, because all of that's underneath now, the Ln of Vt over V0. There we go. Yes, so this R pops up, minus t over C, and then Ln Vt V0 is underneath here. So that's how we can rearrange it, guys. That's how we can rearrange it. Maybe I'll do a couple of videos outlining how to do that as well, so we can look at that as well. Right, so that's how we can rearrange it to make R the subject of the formula. We have to use the Ln functions here. We have to use the Ln functions here. Right, so let's test our understanding and see if we've learned a bit with the following problem. Test your understanding. The initial current for a capacitor with a capacitance of 620 microfarads is 0.6 amps. The capacitor is connected across the terminals of a 450 ohm resistor. Calculate the time taken for the current to fall to 0.4 seconds. So we're searching for the time, everyone. We're searching for the time here. So I'm going to use the current one. So the current at a certain time is equal to I0 e to the minus t divided by Rc. Here we go. Yeah, there is my value of the R, 450 ohms. The value of the initial current is 0.6. Yeah, so let's put that down over here. This is I0. This is R. And we know it's going to be the capacitance. This is going to be C over here. This bit over here is the capacitance value over there. That's the capacitance value. And we're working out the time taken for the current to fall to 0.4 amps. So we're working out the time taken for the current to fall to 0.4 amps. You might want to sketch a diagram very quickly over here so that we have current against time over here. And as you can see, it's dropping down. We know that the current initially is going to be 0.6. So there we go. So this value over here is 0.6 amps. And we're trying to find when it drops to 0.4 amps. So when it's 0.4 amps, we're trying to find out what is this value of the time. What is this value of the time over here? Because we know it's 0.6 at the start, and what is the time taken for it to fall to 0.4 amps. So let's rearrange this formula. So obviously very slowly again. So I'm going to do IT over I naught is equal to e to the minus t over RC. Then I'm going to go for ln IT divided by I naught is equal to minus t over RC times by ln E. And obviously we know that ln E cancels out. Well, not cancels out, that's going to be equal to 1. So it'll turn into 1. So therefore we know that RC times by ln open bracket IT over I naught is equal to t. Yeah, and I'm going to put a minus sign in front of all of this. There we go. It's a minus sign. Yes, because it's minus t, so that's why I took the minus sign across there. So let's plug it in then. So it's going to be minus open bracket the resistance 450 times by the capacitance. The capacitance is going to be 620 times by 10 to the minus 6. There we go, microfarads times by ln of IT, the initial charge, IT, the current at that time is obviously 0.4. So 0.4 divided by the initial current, 0.6. There we go over here. And there we go. That'll be equal to, close the whole thing, and that'll be equal to t over here. So let's do it on the calculator. Let's see what we get. I'm getting the value of t to be 0.113 seconds. Yeah, everyone happy? I'm getting t is equal to 0.113 seconds. Wonderful stuff. So hopefully you've managed to get that actual value over there. Yeah, so 0.113 seconds over here. Obviously you've got to use the ln functions and be comfortable with them. Ask your math teacher for additional support. Okay, so a quick recap from the top. So right from the top, guys, we talked about number 1, using a discharge equation, Qt is equal to Q naught e to the minus t over RC, and using the ln functions. Discharging a capacitor, I had a quick brief recap on that, introduce you to the equation over here, gave you one example. We said that how much charge would be stored on the capacitor after a certain amount of time has passed. We gave you the values of resistance and the capacitance, and we gave you the initial charge, and we said how can we get this actual value, and there we go, plugged it in and we got the actual value of 3.59 times 10 to the minus 29. Scrolling down, we then did discharge equations. I introduced you to the charge, voltage, and current equations for discharge. All of them are obeying the same principles over here. My previous video is more information on that. Scrolling down, I then said to you guys, how do we rearrange it to make one of the exponents the subject of the formula? So look, we've got to use lns here, so make sure you brush up on your math skills. I made r the subject of the formula over here. Make sure you're able to do that yourself. So obviously I ln'd it, and ln e is equal to 1, then I moved the r up, and then obviously I moved that whole thing down underneath the minus t. Then afterwards we did a harder question, guys. Obviously it takes a bit more time now to pick out what I need to do this question. We found out that we can rearrange the formula to make t the subject as well, and we then learned that t is equal to 0.113 seconds. And that's it for another session in CeerazzleDazzlePhysics. Make sure you like and subscribe to keep my channel going, and make sure we teach every child physics for free. Ciao, ciao, and goodbye.